class, this is going to be a little bit of a help session with lab number 11, which is on wildfires, and it's titled Carbon in the Forest. So I'm going to go ahead and skip through the instructions and the objectives and whatnot. I'm going to help you quite a bit with part 1 and some with part 2, I believe. But I'm going to skip through these instructions. Make sure that you do read them though, because they are very important in order to complete what you need to complete. So maybe pause the video, read through the instructions until you get to this bolded section right here. Okay? Okay, so this is where I'm going to help you first. So your goal is to complete the table provided at the end of part 1 or in the Excel spreadsheet attached to this lab, which is on Blackboard. Okay, so I did attach an Excel spreadsheet. I can show it to you in a second. That's where we're going to work. So by following the steps that are outlined here is how you're going to go ahead and complete that table, and then you're going to be able to answer the questions that are below that. So these questions are the lettered questions, and they're not part of the Blackboard quiz questions, but you do need to complete all of these lettered questions, which is A through H, I believe, in order to complete the numbered quiz questions that follow them. So A through G, sorry. Once you have completed A through G, you'll be able to do these numbered questions below. So the table itself that I'm referring to that you need to complete is here at this bottom part of part 1. So you can either do it by hand, you can print it out and do each thing by hand, or you can use the Excel spreadsheet, which is exactly the same table, and that will just simply make it faster. So if you know how to use Excel, it will make doing all of the different calculations much faster. So I'll help you out with some of them so you get the idea of how it works. So let's go ahead and start with letter A. Okay, so use the equation tangent of A times B plus Y to determine the height. So H is to determine the height of the tree, of each of the trees in the plot, basically, and record this on the table. So let's go ahead and pull up the table. Oh, but before we do that, here's a little simplification of why we are using these measurements. So determining the volume of a tree can be complex due to the tree's branches, and as the tree grows, it narrows as it grows taller, right? So it gets thicker and then thins out as it gets taller. So to simplify the calculations, you will simply assume that the tree is a perfect cylinder without any branches. So basically what they're doing is that the branches that are falling off the trees are making up for the narrowing of the tree's main branch. Not the main branch, the stem, I guess the trunk. Okay? So you will also assume that the tree has a constant density, which is also not true depending on which part of the tree you are talking about. So in this case, we are making two assumptions, that the trees are basically cylinders, right? And that second one is that the density is the same throughout the whole tree. So now let's go ahead and pull up the table. Okay, so this is the table. The Excel table that I provide to you, again, is the same one as the one that was on the bottom part of part 1 from your PDF lab file. So first thing we want to do is calculate the height for each of these 17 different trees that you're given. So the formula that they gave us was tangent of A times B plus Y is equal to the height. So we say that this is going to be equal to tangent of A, which is out here. So we say this times B, right? And I guess you can put that in parentheses just to clarify. Oh man. Just to clarify that this is the order of operations, and then you add Y. Alright, so then H for the first tree is going to be 31.42. Alright, so how in Excel you basically have the same operation throughout the whole column is you grab the little cell square that is here on the bottom right, and you drag it down throughout the whole column. And so what that does is that it uses each row's value that you input for the different parts of that formula, right? So as you're seeing, as I'm switching through up here, it will tell you which cell it's using. So as the column changes, each of those numbers on the formula are changing with the row. Okay? Okay. Excellent. So let's go to part B. Okay, so we have determined H. Now B. First, you will determine the volume of the tree and record it in the table. So use the following equation to find the volume of a cylinder. Remember that we had assumed that the tree was pretty much a cylinder, so we're just going to use the formula for finding out the volume of a cylinder. So that formula is V is equal to pi times r squared times h. Okay? So pi we're just going to simply put as 3.14. The radius is going to be, is the radius, and that's equal to half of the diameter of the tree in meters, and you are given the diameter. And then h is the height of the tree in meters, which we just calculated. So let's go ahead and do that. So first we need to calculate the radius, right? Because we don't have that yet. But we know that the radius is simply half of the diameter. So we say radius is equal to d, which is diameter, by 2. Excellent. And so you can do the same thing of dragging this down. Alright, so now we can go ahead and calculate the volume using the formula to find the volume of a cylinder, right? So we know it's pi, and here you have a value for pi itself, 3.1415, so on and so forth. So we use that, yes. Close parentheses here, and then we say times power. So power is going to be a squaring, or not necessarily a squaring, just raising something to x power. So the first thing that you do is you put the number that you want. So we want the radius, and then you put a comma, and you set the power that you want. So we want the radius squared, so radius squared, and that you multiply times the height of your tree, which we have already calculated that up here. Excellent. So the volume for that first tree is going to be 24.67 meters cubed. All right? Okay. So now let's go on. So remember again, you can draw these formulas down on the rest of the trees. All right, let's go to C. So C says, next you will determine the oven-dried biomass, otherwise called B for purpose, or the weight of the tree, not including the roots of it. So record this value in the table. Use the following equation to find the oven-dried biomass. So we're going to use B is equal to volume of the tree times S, which is going to be the dry specific gravity of wood per tree type. So that's going to vary between the different types of tree that we have, times the weight. And that's the weight of 1 meter cubed of water. So that's 1,000 kilograms. Okay, so let's go ahead and input those values. Again, the specific gravity is going to vary depending on the type of tree that we have, so we have to be considerate of that. The values for the different trees that we have are all specified here, so we're going to have to refer back to this table, table 1.1 of your lab, a couple of times. Okay, so we have B above ground in kilograms. So we said that that was going to be equal to the volume, so in this case that's that value, times the specific gravity, which is not given to you in this table, but it is given to you here for the specific type of trees that we're talking about. So the first tree that we have is a white pine, W white pine. So let's look for that value in this table. So the western white pine has a specific gravity of 0.38. So that's what we'll input into the Excel formula. So 0.38 times the weight. So remember, the weight of water, of 1 meter cubed of water, is 1,000 kilograms. So we'll leave it as that. And that's going to be the value for the oven-dried biomass for that first tree. So 9,378 kilograms. All right, so as you are doing this, you can't simply use the dragging down function, because the specific gravity is different for each type of tree. So you can do it for all the western white pine trees, but then once you get to the ponderosa pine, the specific gravity number is going to change. And then once you get to the lodgepole pine, same thing. So be mindful of that when you're doing it. Okay, so let's get down to the next one. So D, it says, so next you will determine the total weight of each tree, the above ground portion of each tree, and the root portion of each tree. So that's going to be the total weight of each tree. They assume that the root system here weighs about 20% as much as the above ground weight of the tree. So therefore, to determine the total weight of the tree, simply multiply the above ground weight of the tree by 120%. So 100% of it would be its weight, its value for B that we had just calculated. And then the remaining part of the roots is going to be an extra 20%. So you have to multiply this times 120%, meaning simply by 1.2. Okay? So that's how we're going to multiply, or that's how we're going to find the total weight of the tree, by multiplying the number that we just got for the oven-dried biomass times 1.2. So let's do that. So total is going to be B times 1.2. Okay, that was straightforward. And that you can drag down without any problem. All right, next question. So we have E. Next, you will determine the weight of carbon in the tree, which is the C content as the table refers to it, okay? The average carbon content is generally 50% of the tree's total volume. The rest of the weight, just for your information, is taken up by all sorts of other elements, by water, by air, by all sorts of other things. So about 50% is carbon, the rest is other stuff. So therefore, to determine the weight of carbon in the tree, simply multiply the dry weight of the tree by 50%, which is the same thing as dividing the total weight of the tree by 2. Okay? So we're going to go ahead and do that. So we have a total weight right here for the tree, and we simply want to divide it by 2. That's going to give us the weight of the carbon. Excellent. Straightforward. Next question. So next you will determine the weight of carbon dioxide sequestered in the tree, and later record these values in your table. So this is a little bit more complicated. So let's just go through it. So carbon dioxide is composed of one molecule of carbon, right? So carbon, and then 2 of oxygen. Perfect. The atomic weight of carbon is 12 point something. The atomic weight of oxygen is, we round it out to 16. So the weight of carbon dioxide is 1 of carbon plus 2 of oxygen, which is equal to about 44 values or units. So the ratio of carbon dioxide to carbon would be equal to 44 divided by 12. So that's how much carbon there, or how much carbon dioxide there is in reference to how much carbon you have. So there's 3.6 times, or 3 close to 7 times as much carbon dioxide as there is of just simply carbon. Okay? So therefore, to determine the weight of carbon dioxide that is sequestered in the tree, what you need to do is to multiply the weight of the carbon in the tree times 3.6663. So hopefully that made sense. If it didn't, reread it a few times. If you have any questions, let me know. But let's go ahead and do that really fast. So we say that this is going to be equal to the weight of the carbon in the tree times 3.6663. Excellent. Okay, so now we go ahead and finish with letter G, all the lettered part of the, questions of part 1. So we say, next you will determine the weight of carbon dioxide sequestered in the tree per year. So divide the weight of carbon dioxide sequestered in the tree by estimating age of the tree. So to determine that, you do in order to determine the amount of carbon dioxide sequestered by each tree every single year. And we will record that in the table. So we already have the weight of the carbon dioxide sequestered in the tree, and now we just have to divide that by the age of the tree itself. So in that cell, we're going to go ahead and say, okay, my CO2 sequestered per year is going to be equal to my CO2 sequestered divided by the age of my tree. So that is this column here, all the way to the left. Boom. Alright, so that is how we get the table filled out. And again, remember to fill all of the values that you have for all of those 17 different trees. Okay? Alright.